There we go. It's just recording. We have the relationship acceleration dv dt times the unit vector plus v squared over rho, and that's for the normal vector. And so that's your defined relationship. And then the velocity, of course, is just v times the tangential unit vector. So there we did the derivations. I'm not going to go over that again. And so we did this example last time where we talked about which one had the greatest acceleration, which made sense because it was the one that had the sharpest curve or the smallest radius. Okay, so where did we leave off? So what I want to do now is we talked about the theory and the equations. I would write those down, have them in your notes. For an exam, I will allow you to have a note sheet, so it's not as though you have to memorize any of these equations. I'm not a big fan of that, but I do want to go through this example and another similar with polar coordinates, just so that you're familiar with that. And we're just about then done with chapter 11, and then we're going to start at chapter 12, which is a little different than what we've been doing. Start talking about F equals ma and Newton's second law. All right, so here in this example, we have a particle P, and how it's connected to a robotic arm, but that's immaterial. All we know is that P is traveling in a circular pattern. And so we can model it as a particle. Its radius is 0.8 meters or 800 millimeters. And we know that when it starts from rest, its speed increases at an acceleration of 10 millimeters per second squared. So that's our tangential acceleration. And so what we want to do is determine the magnitude of the acceleration when t equals 4 seconds. And the time for the magnitude acceleration to reach 80 millimeters per second squared. Okay, so let's go ahead and walk through that problem so we understand what we're doing. Now, oops, there we go. And so we know that we have a particle P up here, and we know we have it's moving, and we're given that radius is 800 millimeters. I'm just going to put it in millimeters. Sorry, it's a little, see if I can get this to focus better. Well, it's awful. That's better, but much. Let me. I think it seems to focus better on this type of paper because it has something to grab hold of. So let's do it with this. So we have, again, we have our circle and we have our particle P. That's the main thing. So we know our radius. So we're given that our tangential acceleration is 10 millimeters per second squared. All right, so we have that. And then so we'll start with that. So we also know that our normal acceleration is just going to be equal to our velocity squared over our radius. So at t equals 4 seconds, we know that velocity is just going to equal the acceleration, 10 millimeters per second squared, times the time, or 4 seconds. And so we get a velocity of 40 millimeters per second. So if we go ahead and calculate our normal acceleration, that's just going to be 40 squared over 800, since we're in millimeters per second. So this is millimeters per second, and that's in millimeters. And so that's what I want to do. We want to keep the units consistent. So this gives us a value of 2 millimeters per second squared. All right. Now we're asked to find the acceleration. Now, and so whenever you're dealing with this, you want to make sure that you recognize that acceleration is actually two components. The acceleration is equal to, it's a vector, and it's equal to the acceleration tangential plus the acceleration normal. And as a vector, it'll usually have some unit vector over here. So we call that, if we rewrite it, it's acceleration times E tangential plus acceleration normal times the normal vector. All right. And so, but what we can do in this problem is we're not asked as a vector, but we just want to know the total. So then we can just use the Pythagorean theorem, and we know that A is just going to be equal to 10 squared plus 2 squared square root, and we get an A equal to 10.20 millimeters per second squared. Okay, so that's our acceleration. So that's part A of our question. So in part B, we want to know the time when we are at acceleration equaling to 80 millimeters per second squared. So I know when is that. So we know that a squared equals normal squared plus tangential squared. And so we're going to have to do a little substitution. Well, since velocity equals tangential times time, right? So that's how we learn that up here. Let me make my, not so cryptic. So acceleration tension times time, then that's velocity, and we know that velocity the acceleration normal equals velocity squared over rho. Then we can plug this into here, and we know that acceleration normal is just going to equal the A tangential squared times time squared over rho. Okay. So now we have a relationship for that that gives us just t in terms of t. So if we do that, we go back over here and we say a squared. Well, we know a squared, the total that was given to us as 80, right? We want to know when that's 80. So we say 80 squared, and then that's going to equal this relationship. So a tangential squared times time squared over rho, all of that squared, and then plus our a tangential. Now our a tangential doesn't change because we know we're at a velocity, and so we can just assume that that's 10, and that's going to be 10 squared. So if we solve, we end up with 6,300 equals and we plug in 10 for this. Sorry. Yeah, sorry about that. If we do 6,300, that's that, and then we substitute in this value here, a tangential, 10 squared times t squared all over rho, which was 800. And then we square all that, and that's 6,200 because we moved that to the other side, and then we solve for that, break that down, we end up with basically 6,300. Sorry, put up 6,300 equals about 0.015625 t to the fourth. So if we solve for t, we get t equal to about 25.2 seconds. All right. So again, it was a fairly easy example because all we were using is tangential and normal. There was no integration. We just had the direct calculation. So it made life a little easier. Now, if we go back to this screen. I'm going to skip this problem. Last class, I didn't have time to come back to it, but this is just a relative velocity. And we've done quite a few of those, so I'd rather move ahead on some other material. So what I'd like to talk about now is polar coordinates. So you remember this from math. I think it's 143 where they introduced this. Even after all these years, I took Calc 1 in summer of 1988, and probably well before any of you were alive. But I still remember what each 142 is techniques of integration, 143 was power series, and then 241 was triple integrals and other weird stuff. So within this, there is a derivation for these two equations, and I don't expect you to derive them. They're not that hard to derive, but I don't see the advantage to doing it. So, but you do know that if you're going to describe velocity in with polar coordinates, you have essentially the time derivative of r times its unit vector plus r times the time derivative of theta times its unit vector, and then acceleration is just similar. It's the second derivative of r minus r times the derivative of theta squared times its unit vector, and then plus r theta double dot plus r dot theta dot. And so in solving these questions, generally what we do is we give you the equations for them, and then it's just usually how difficult is it to differentiate. So, I mean, some of them I've seen are very challenging. They can be done, but it takes a little bit of effort to do them. But once you have them, then you're just given conditions, you plug in numbers and you get the answer. So overall, I think they're more calculus than they are dynamics. And so we're going to limit what we do to it, mainly because I want to stick to dynamics in this class. So those are the two equations. I would write them down, have them. You'll be using them again. Don't have to memorize them, but they'll be useful in tests.
What are the dots?
Those represent the derivative. So r dot is the time derivative. So that would be r dr dt is r dot, and then the second derivative of dr dt is r double dot, and that's just a frequent notation that they'll use. All right. So also you can use what are called cylindrical coordinates, which you may remember from calculus. And so then we add this extra term here. The position vector has the z term for that dimension, and then the velocity has the time derivative z and then time derivative double z in both of those. And so this is about as simple as it gets in 3 dimensions, but we will not be dealing cylindrical in this class, as far as I know. I think you'll be seeing that if you take intermediate dynamics, but I don't believe you'll be dealing with that in here. Okay, so what I'd like to do is an example. I guess it doesn't matter what I like to do. I can do whatever I want. So powers of being the teacher. But what I'm going to do, I should say, is an example of using polar coordinates so that you can understand how they're utilized and what they mean. So in this case, it's a fairly simple example. You have this rod that's rotating about a fixed axis O, and the angle theta is what is swept by the rod. And this collar B freely slides up and down R without any friction. And so we're given that the theta equation with respect to time is just t cubed. And so that's just time cubed. So it's saying that that's the position according to time. And then we also have the collar's position r is 100 t squared, where both t's are in seconds. So we're going to go ahead and figure out what is the velocity acceleration of this collar when t equals 1 second. And so this is fairly straightforward problem, because really it's just a matter of using the equations, taking the derivatives and solving. So let's look at that. So we have, and when I'm done with the calculation, then I'll show you the actual drawing, so I don't have to redraw it here. But remember that we have our equations, V equals R dot, and then times the unit vector, plus R theta dot times E theta. And then the acceleration is equal to R double dot minus R squared, and then plus R double dot plus 2R dot theta dot, and then that's all times its unit vector. Okay, and so we're given that theta is equal to t cubed. So that means that theta dot is just going to be equal to, and that's going to be, we'll just leave it at that, but then that's going to be 3t cubed. That's going to be, and then we take the second derivative, that's going to be equal to 6t. And that's it. I'm not 3t cubed, sorry, 3t squared. And then that's just going to be equal to 6t. If we do the same thing for r, we're given r is 100t squared. And then r dot is just going to be 200t. And r double dot is just going to be equal to 200. Okay. So all we've done is figured out those with the simple equations that we've given. So now at 1 second, we can figure out what all these are. So we know that 1 second, this is going to be 1 radian, because that's what the units are for theta. We know that this is going to be radians per second. So that's going to be, if we substitute in 1 second for that, just going to be 3 radians per second. And if we plug in that, that's just going to be 6 radians per second squared. For R, similar, we're going to get 100 millimeters. This is going to be 200 millimeters per second. And this is going to just be 200 millimeters per second squared, not a function of time. So now it's just a matter of, because we know what each of these are, sorry, this should be double dot, sorry about that, then we can just plug them into their respective places up here and put in the numbers and solve. So pretty straightforward, even though the equation looks somewhat complicated. So if we do that, we end up with, for velocity, we'll do velocity first. We end up with r dot, so that's just going to be 200 times the unit vector, and that's going to be plus, and what do we have? We have r dot times theta dot squared. So, no, I'm sorry, r dot theta dot. I'm sorry, I was looking at the acceleration. So r dot, so that's just going to be 100 times 3. And so E theta. So our final velocity then as a vector is just going to be equal to 200 E R, and then plus 300 E theta. Okay. Now, what does that look like if we look at our diagram for that? Then this is what we get. So this is our original drawing, and then here's the drawing with the actual collar. So we know that theta was just 1 radian. So we know that that angle there is 57.3 degrees at 1 second. And then we know that the collar consists of a radial and that the two directions that we have. One's in 200 millimeters per second, and this one over here is 300 millimeters per second. And so I should have put, there we go. And so if we take Pythagorean theorem, then 200 squared, 300 squared square root gives us 361. So that's our magnitude. So that's really the velocity direction of the whole thing. And then we could figure out using tangent this angle. And so we have this angle plus this angle because this is our reference. And so the total angle would be 114 degrees. So remember, when you're presenting data, or I'm sorry, when you're presenting these numbers, velocity, you can present it either like this as a vector, or you can present it like this with the magnitude and direction. Now, on an exam, if it was a problem like this, I would not expect you to take the extra step here. You know, usually I say whatever easier. So you'll notice that sometimes we solve problems with triangles, in which case we get the magnitude and the angle. It's real easy. I know you can go back and forth easily. I don't need you to spend the extra time on a test showing me. So most likely to just give me this. Okay. So now next step is, what is the acceleration? And do that pretty much the same way. We have, here's our equation up here. And let's see if I get this thing to focus. That's something to focus on. So now if we want to put in our acceleration, then we just plug in our numbers. So now we have A equals, and I guess we should see these and make it a little easier. So we have our numbers. So it's just a matter of plugging them in. So A equals 200, that's R double dot, minus 200, I'm sorry, times, no, 100, that's R, just R. So 200 minus 100 times 3 squared, and that's E R. And then that's going to be plus 100 times 6 plus 2 times 300. No, it's 200. Is it 300? 200. Oh, it's R dot. Sorry, I'm just looking at something else. So it's 2 times 200. Again, just pulling our values from here. So we get 2 times 200, and then times 3. And then that's all E theta. So we simplify, we get essentially negative 700 ER plus 1800, not 188, plus 1800 E theta. And that's in millimeters per second squared. So if we take our angle, we get about 68.7 degrees. And so if we show this again, same way, when we draw it, so here's where I worked it out, put this in, put in our numbers, we got that plus that, gives me this. And then if we plot, we have still the 57.3, but now our acceleration is going backwards or in the opposite direction. And so now if we add this and this together, the total angle is going back that way. So in order to get the angle, I have to subtract 180 from it. So this is actually saying phi, which is the angle that this is going in, is equal to 57.3 plus 180 minus 68.7. And so we get 169 degrees. And that's it. And that's all there is to this one. So this one was just simply filling things in. Remember that the scalar components are just taking the vector apart. So, you know, here we have that. So the scalar components, this and this. So down here we have R dot, R theta dot, and then respectively for radial and theta. Okay. If we're moving in a circle, we know that these two are 0. That simplifies it a little more. And then these were just the equations that I showed when you have it in space. So you have to add the Z component in, but we're not going to deal with that at this point, if ever. Okay, so let's look at another problem that's similar, and it's so here we have a similar problem in the sense is that we're using polar coordinates. We have a pin P that moves along the curve shown. And so that curve is defined by that equation, R equals 4 sine 2 theta, and that's in feet. And then we're just given the arm rotates at the constant angular velocity of 1.5 radians per second. So how do we solve that? So in this one, we first we know what R is. So, and we know what theta is. We're given, well, we know theta. We know that theta dot, sorry, not theta prime, is 1.5, right? Because the angular theta is, and then you take the time derivative, you get 1.5 rads per second. So let's write that down. So if we do that, we know that theta dot is just 1.5 rads per second. Therefore, theta double dot is 0. Okay. Then if we write our R, just like before, we first figure this out. We have 4 sine 2 theta. And then if we take the time derivative of that, we get 8, and we use the chain rule. So we get 8 cosine 2 theta times theta dot. And that's in feet per second. Okay. And then we take the next derivative, R double dot, and we get 8 times cosine 2 theta times theta double dot. So that's in there. And then that's going to be minus 2 sine 2 theta. And then that's times theta dot squared. And that's just taking again. And then that's all in feet per second squared. Okay. So you can see that the more complicated the function, the harder the derivative will be. But again, I'm not going to test you on your calculus prowess. So if I want you to do something with this, if it's something that's not an easy derivative, I'll probably just give you the derivative and then you can use it from there. Because again, you already had calculus. I don't want you spending 20 minutes on a test doing it. All right, so if we go ahead and now we want to solve, then this one's kind of plug and chug also, because we know that we're given that our angle is just 60 degrees. And so what we can do is we can just say, well, what is R? R equals 4 sine 2 cosine, 4 sine 2 times 60. Just using the equation that we started with. And so that gives us an R equal to 3.464 feet. Or with sig figs, 3.46 feet. And then if we do R dot and we plug in everything, we get 8 times cosine, and I'm just going to say 2 times 60 or 120. And then that's going to be times 1.5, because that's all multiplied by theta prime, or theta dot, sorry, and that's 1.5 radians per second. So we end up with R dot equals a -6 feet per second, and that's because cosine of an angle greater than 120 gives us a negative. Then if we do R double dot, we put it all in this equation again, and so if we do that, for one is we know that this is 0, so that first term disappears, so we can cross that out here. And then we just have this, so we get minus 2 sine 2 times 60 times 1.5 squared. And so we end up with R double dot equals negative 31.18 or negative 31.2. Okay. So taking that, we know that if we want acceleration R is just going to equal R double dot minus R theta dot squared, which is just really negative 31.18 minus 3.46 times 1.5 squared, which gives us a negative 38.97, or essentially negative 39.0 feet per second squared. So this, again, what are we trying to find? We're trying to find acceleration of p when theta equals 60. So first we had to find these. Now we're finding that. So we got the radial, and then we'll get the other one, the a theta, and that's just going to equal to r theta double dot plus 2r dot theta dot. And so again, that's 0. So you get 2 times 6 times 1.5, and that's going to be equal to negative 18.00 feet per second squared. And so if we want the acceleration, again, that's the total, and that's going to be equal to the magnitude, or negative 38.97 squared plus negative 18 squared, and then square root. And so the final value we get is 42.9 feet per second squared. Okay. So move that up a little. So again, you notice that you just had to plug those in. Now, there's more complex things we can do with them, but again, dynamics, even though it doesn't seem like it's kind of a survey course because we're going over a bunch of different stuff. Now, one thing, let's see what that piece of paper. Yeah, what I did want to show you is to kind of understand this all in general. If we think about polar coordinates, you know, we have our velocity equation. So this represents radial velocity. That's transverse velocity or tangential velocity, which I've been saying. And so that's how you can, if you see this written in the book, then you know what it's referring to, because sometimes it can be confusing as to what they're talking about. But this is pretty universal, these two terms. So then if we look at acceleration, if we break that down, then we know that r double dot, because it's d2, it's the second derivative of r, that's our linear acceleration. We know that this term here is our centripetal acceleration. We know this term here is our linear acceleration in the tangential direction, because it's, again, the double derivative with respect to time. And then the last one is our Coriolis acceleration. Okay, that's just what it's called. So that kind of gives you an idea of what you're seeing. All right. Any questions on anything? Clear as mud, I hope. All right. So let's, what I want to do at this point is I'd like to talk about chapter 12, since we're pretty much at the end of chapter 11. We've pretty much gone over everything that's important in it. So chapter 12, Newton's second law. And so that deals with F equals ma. So we'll be using that in many different iterations. The important thing is in this chapter, we're going to add a type of diagram that we haven't done before. So we started with the free body diagram. Now we're going to add what's called a mass acceleration diagram, or sometimes a kinetic diagram, as in your book. And so this is just describing what F equals ma is, just a definition. So here we have linear momentum. Now we'll get more into momentum, and I am not really skipping around the book, but I am going to jump ahead a little bit because I want to do linear momentum first and then come back to angular momentum. And so parts of those are different chapters in chapter 12 and chapter 13. So it should make sense though once we're done why I separated them like that. But we know that if you take the time derivative of mass times velocity, you get the linear momentum of a particle. Remember from physics that momentum is just mass times velocity. And so usually when I remember teaching physics many years ago, it was P equals mv. So we always use the letter P for it. But in this case, it's still essentially the same thing. And so this is just saying that if you sum the forces in the X and the Y and the Z, you're going to get a sum of the forces equaling MA in the X, MA in the Y, MA in the Z. So nothing really new there. Just like in statics, we sum the forces in each dimension, and that's how we keep track of everything. So we only are concerned with forces acting in a particular direction, and then we can treat them as separate entities using the Cartesian coordinates. Now, this is free body diagram. This should be review. I know that everyone's taken statics. If you've had me for statics, you did quite a few free body diagrams. I wasn't super retentive about them in statics, but I am going to be much more so in this class because it is so important that you get the free body. Also, not just correctly, but neatly. So if they remember, using a straight edge is your best friend. You need to have some kind of a ruler or something so that your drawings are good. So I'll be looking for that when I grade your homework. So this is should be pretty much review though, how to make a free body diagram for this. So so here you have the free body, and this would be what I consider the left side of the equation. This is the F. So these are all the forces acting on it. And then you go to what's the MA, or the right side of the equation. So here we have the FBD on the left, and then on the right, you have the kinetic, or the mass acceleration diagram, or MAD for short. So kinetic diagram, mass acceleration diagram, same thing. And so there you're going to draw your mass time acceleration of your particle, depending on what it's doing. So oftentimes we're going to start with objects sliding down inclines, and you probably did some of that in physics, but we know that in that context that the acceleration of the y is usually 0 if we tilt our axes. So here, if we look at something a little more complicated, I mean, we're looking at block A, we've isolated it. So the important thing is that you recognize everything that's acting on it. It's not really complicated because you can see that the tensions, some of them are internal, but you have the tensions all noted. You have the normal force from block B, its friction force. You have the friction force from the incline on it on block A, and then you have its normal force respectively. And then if you look at the kinetic diagram, it's fairly simple. You just have mass times acceleration down the incline, and then the 0 up the incline. So here's a conceptual question. And so if you have this truck, and say it's standing still. And so you start off with it standing still, and you know that the box B, the boulder B weighs 1,000 pounds, and it's on a 200-pound platform. So it makes sense that just summing the forces would give it that the tension has to be 1,200 pounds. So now, assuming that, of course, that you start moving, and we have a frictionless pulley. And then the question is, what's going to happen to the tension? So first, A, is the tension going to be 200 pounds? Well, no, that's silly because you have 1,200 pounds on it. Maybe if you were cut the rope at some instant, it would be. The other thing is the tension, the cord connected to the truck is 1,200. Well, it's 1,200 when it's not moving. But think of like an elevator. When you get in an elevator, especially if you're going, some elevators have a little more kick to them, acceleration, than others, but especially in foreign countries, they're not widely regulated. But you'll get in it and it'll take off, and for an instant you'll feel fairly heavy. Your body will actually sag a little because you're suddenly, you're feeling the effect of the acceleration. So that, in a sense, you have more weight to you at that moment. And so the same thing is with this truck. As this truck drives away, the tension is actually increased because there's inertia to B being at rest, and you have to accelerate it. And so it's going to be make the tension greater. So the answer C, the tension of the cord is greater than 1200. You probably figure that out. And then the other part is about the normal force. Well, we know the normal force, we don't know it's going to be 1200. We have a way to calculate that, but we do know it's going to be greater than 1000 pounds because as the cord takes off the same thing, the relative weight of B is going to seem greater to A due to the acceleration upward. And then we have another question here. We have these two blocks. We have two blocks that weigh 40 pounds, and then we have a block with just a 40-pound force on it. And so we want to think about, well, if the system on the left starts to move, assume it's frictionless, then we know that A is going to start to accelerate to the right. But when we write our equation, the sum of the forces, and this is going to equal A MA. Well, M in that context is going to be 80 pounds, isn't it? So there's more inertia in the left. Whereas in the right side, you just have a 40-pound force pulling down. You're not actually moving anything. The other thing to think about is that the instant you start accelerating A, that tension, that cord is not going to be 40 pounds anymore. It's going to drop due to the acceleration, just like the same way the tension in a cord would drop as the elevator slows down as it reaches the top. So it makes sense that block C will have a larger acceleration than block A from both the inertia standpoint and the total mass of the system, and the fact that the tension is going to drop. The 40 pounds won't be 40 pounds upon an instant acceleration, but the 40 pounds on the right will remain 40 pounds. Okay. All right, so last thing, objects A, B, C have masses MA, MB, MC respectively. They have a kinetic friction between A and B is kinetic, and the friction between A and the ground is negligible, and the pulleys are massless and frictionless. So assuming B slides on A, draw the free body diagram and the kinetic diagram for each of the three masses, A, B, and C. All right, so this one, since we have a couple minutes left, I'd like you to take a couple minutes and try to draw them. So it'll be to your benefit, but go ahead and draw. So think of A as its own unit, think of B as its own, and then think of C as its own. So first draw the free body for A, B, and C, and then draw the kinetic diagram for A, B, and C. And in a couple of minutes, we'll go ahead and I'll draw it for you, and then you can compare to what you got. Okay, so let's go ahead and look at what we had. So, so here's what I have for it. And so the top one, tension, you have the two tensions there. And then you have, of course, the normal force from B pushing down. And then to the right, to the left, sorry, you have mu static times normal force B. Okay, so that's all that's acting on this. And then you have, of course, mass times acceleration x, and that's it. And the reason you don't have anything here is because it's frictionless, okay? And so then you also have for the block B, that will give you normal force B, mass times B, gravity, mu static NB, and then tension here. And then our mass times acceleration is that's our kinetic diagram. And then lastly, we just have for that hanging tension, mass G, and then our kinetic is just mass times acceleration. So hopefully that makes sense to you guys. Practice is going to help, but we're out of time. So as I was saying, I'll see you guys Friday in class, and I would try to work on the homework between now and then. We'll jump in more into chapter 12, but otherwise I'll see you guys then, and thank you for tuning in.
Thank you.